Okay. Yes, okay, so the first remark to make is that in the first type, these have already been classified, so they're due to Diarra. I forgot exactly when, and he showed that they exist only for n is at most 6, so only p1 minus 6 points. And yeah, I think Diarra fully classified these, but there are a lot of previous examples due to Kitaev and Chakdor. Okay, so yes, again, this is the theorem. Okay, I should also say the last thing is U is attached to a finite group. So this finite group also has to be very special. So it's what's called a complex reflection group. So the definition is like this. If you have any element inside GLN, we call it a pseudo-reflection if all but one of the eigenvalues are 1 and it has finite order. Okay, so I really, there should be an extra condition here, which is that A is finite order. Okay, so basically all the eigenvalues are 1 except a last one, which is a root of unity. And a finite group is called a complex reflection group if it's generated by these pseudo-reflections. Okay, so usually if you take a bunch of pseudo-reflections, they'll generate an infinite group, but in some cases you just get a finite group. So this won't be too important for the rest of this talk, but it's just to say that these complex reflection groups are very constrained. So they've also been classified. So this was done by Shepard and Todd. So the classification is something like this. There's some infinite family, GMPN, depending on 3 integer parameters. And then there are some 34 exceptional ones. So you already know, like, a lot of these, like if you have the icosahedron, you can look at reflections or symmetries of the icosahedron, and that would be a complex reflection group, or you can just take any Var group. And of course, as you know, those are generated by reflections, so that's also a complex reflection group. And then there are some more exotic ones, which I don't really know how to describe, like a Valentinus group and a bunch of other things. But in any case, they've been classified. So in this sense, you can really get your hands dirty once you know this theorem. You will be attached to one of these finite groups, and you just try to find a representation into the finite group, like a Valentinus group, and then apply middle convolution to it and see what happens. Okay, so this is the example from before, so let's revisit it. So this will fall into the second class, so it should correspond to some finite complex reflection group, and the point is that all of these correspond to the dihedral group. So here, GLN should just be GL2. Yes, and okay, so our theorem gives it gives a constraint on what these algebraic solutions are, but you also have to fully classify them. You have to get your hands dirty and see what's going on. So we also found a bunch of other examples, like ones corresponding to the icosahedral group, and so on.
Just this example has to do with the monodromy of the Gauss hypergeometric function, or
not really. So yeah, what should I say about this?
I guess they're Lemay equations, right?
No, I mean this is
these are not
3 singularities, so it is. I mean,
it is four.
No, there are 4 singularities. Sorry, yeah, all of these are p1 minus 4 points.
Okay. Okay. So how you don't write the other one because okay. Sorry.
Yeah, I was lazy. So yeah, that's the 4th matrix, which is like the inverse of the product of these guys.
Okay.
yeah, so it's on pure minus 4 points, and it corresponds to algebraic solutions to Painlevé VI. Algebraic solutions to Painlevé VI, and these solutions are called the Cayley solutions, perhaps. Yeah. Are there any other questions? Okay, so let me say a word about what the previous work on this is. So again, all the previous literature is basically in the case n equals 4. So again, this is the Painlevé VI case. And in this case, x4, you can write it as basically this affine surface. So here, A, B, C, D will correspond to the parameters in the Painlevé VI. So Painlevé VI has 4 parameters. And this is the equation of x4. And there'll be a braid group action. And the question is to classify the finite orbits of the braid group action. So we looked a little bit at the history of this. So this surface is called the Fricker-Klein surface. But really, the dynamics was first studied by Markov. And then there's a huge amount of subsequent literature on this dynamical system, like due to Goldman, Conta, and Loret, and so on. And then algebraic solutions to Painlevé VI, well, are due to many people. So Kitaev, I already sort of mentioned with these pullback solutions, and so this work, Andreev and Kitaev, Philip both has done a lot of work on this, Doran, more Kitaev, and Hitchin. But the kind of most relevant thing is a work by Dubrovin and Masako, and I'll say more about that in the next slide, I think. And those were only very recently shown by Lesofi and Tiki that this was that all the solutions have been found. So the full classification of Painlevé VI algebraic solutions is known, and it was done by finally by a computer search by Lesofi and Tiki, and this was around 2008, I think. Okay, so as I say, this is this beautiful work of Lesofi and Tiki, where they classify all algebraic solutions to Painlevé VI. There's this previous work of Dubrovin and Masako, like almost 10 years earlier, where they classify the solutions, but with some conditions. So again, this is Painlevé VI, and they put the constraint that I think A1, 2, 3. So these 3 matrices are in the conjugacy class of 1, 1, 1, 0. So they take this conjugacy constraint that they're unipotent, and after that, they classify all these solutions. And it's really an amazing work, but their approach is very different from what we do. Okay. So, okay, let me kind of digress into some more algebraic geometry, because this is how we prove the theorem. Okay, so again, I have a local system. So a priori, it's a local system on an algebraic variety. And a priori is just something topological. So we say it's of geometric origin if it comes from a family of algebraic varieties. So in other words, there is a family of algebraic varieties, pi, from y to x. And V is obtained as the solutions to the Gauss-Manin equations. So V is the summand of this higher direct image. Okay, so these are kind of very special local systems. And the corollary of our work is that we can classify all rank 2 local systems of geometric origin on this generic p1 minus endpoints. So we don't know about just any p1 minus endpoints, but if you just have a general p1 minus endpoints, then we'll classify them. And again, assuming this condition that AI has infinite order. And the classification is, as before, either is of pullback type or is this middle convolution. Yes, this is what I said. Okay, so I already said a lot about middle convolution, but without telling you what it is. So let me say a few words. So it's not so complicated. So let me say a few words. So first, this was invented by Katz around 90s in his study of what's called rigid local systems. So this is MC, and it depends on chi, where this chi is some complex parameter. So what is it? So essentially, it produces new local systems on our usual guy X, which is P1 minus endpoints, from old ones. And the way this works is some kind of analog of the Fourier transform. So basically, we have our X here, and we consider the product like this. And MC chi of V. So V will be the old local system we started with, and MC of it will be some new local system. And it's kind of a usual formula. We first pull back to the product, pi 1 up a star. And then this parameter, chi, will give another local system on the product itself. So then we can tensor by it and then push forward. So this equality is kind of in quotation mark, but very roughly, this is what it is.
Sorry, so I think maybe there's some that push forward should be derived. Maybe there's some parenthesization.
Yeah, this is all very. Yeah, I can derive this if you want.
Yeah, but I think there's also the parentheses should be pi 1 upper star V tensor chi in parentheses. Anyway, sorry.
Oh yeah, that should be this. Yeah. Absolutely. Yes, so this is what it is. It's kind of, yeah, it's actually easy to understand this in terms of the differential equation, and it's really quite close to a Fourier transform. Okay, and the key point is that MC chi will commute with the braid group action. And so if you black box all of this, then MC chi of MCG finite, well, maybe let's just say something with finite monodromy. Is MCG finite. Okay, let me explain this a bit. So as I said before, if you have a local system with finite monodromy, then it's automatically MCG finite. And because MC will commute with the braid group action, so just respect the braid group action, once you apply MC, it will still be MCG finite. It might no longer be finite monodromy, but we don't care about that. So anyway, this is a way to produce a lot of MCG finite local systems from old ones. And Katz was very well aware of this. Okay. Oh, are there any questions on this? This is quite technical.
Just maybe one question.
Yeah.
Do you think any MCG finite is obtained after a lot of middle convolution?
Yeah, so that's a great question. So yeah, so thank you for the question. It's almost like I set this up. Yeah, so from our theorem, it might seem that this is the case. And in rank 2, that is basically the case. And so let me say maybe a little bit more precisely, if you start from something with finite monodromy, then you can apply this middle convolution, and you get something still MCG finite. After that, you can like tensor it with a rank 1 local system, and then apply MC again, and so on and so on and so on. So you get many of these MCG finite local systems. You can ask, is that everything? So that's what Hussein is asking. And for a while, we thought maybe this is yes, and we tried to prove it, maybe for like rank 3 local systems. But unfortunately, yeah, this is just not true. So there's some quite subtle invariance which prevents this from happening. Yeah, it's a bit too much to go into what that is, but we can discuss it afterwards if you're interested.
Maybe the smallest counterexample we know is rank 6 or something like that.
Something like that, yeah. Yeah, so thanks a lot for the great question. Okay. But I should say, of course, what Katz does is that in the case of rigid local systems on P1, then you do get everything in this manner. Yeah, so that's also one reason why we thought maybe it's true. But unfortunately, life is not so good. Okay, so now let me say a word about the proof of the main theorem. So let me remind you what we're trying to prove, and it's just that, well, basically, cartoon version is that any MCG finite rank 2 V is two things: pullback type or MC of something where U is finite monodromy. Okay, so that's what we're trying to prove. Okay, I think. Okay, so the first thing to remind you is that an MCG finite local system can be extended to the universal curve or some cover of the universal curve. Okay, so let's just pretend we have a local system V tilde on this universal curve, or maybe some cover of it, doesn't matter. And so there's this very remarkable theorem of Collette and Simpson, which basically gives this dichotomy. So there's two cases. So V is either pulled back. This should say V tilde, right? This V tilde, which is the thing on the universal curve, is either pulled back from a fixed curve or it's of geometric origin, or both. Okay, could be both. So sorry, again, this is V tilde. So we apply the theorem of Collette and Simpson, of course, and you just check that the first type are exactly those classified by Diarra. So there's a little bit of content there, but it's not so bad. So the interesting case is to try and classify those of geometric origin, so those coming from a family of algebraic varieties. So here's the claim, and this is the main technical result, which I won't really tell you how to prove. And the claim is just that you can always find a character chi, or really this is just a complex number, so just think of it as a complex number. So for each complex number chi, there's this functor MC chi, middle convolution, and the claim is that you can always cook up this number chi so that MC of chi is a unitary local system. So in other words, this has a unitary metric, which is preserved. Okay, but not only that, but also the same for all the Galois conjugates of V. So V will be some local system. You can take a Galois conjugate if you apply an automorphism of C. And this is our main technical claim. Okay, so assuming this, we can just basically conclude, because if you look at this MC chi of V, well, not only is it unitary, but all of the Galois conjugates are unitary. So if you look at the whole sum, so I just added to all of this Galois conjugates, it's both integral, because of geometric origin, and unitary. And so the monodromy has to be finite, because it's discrete and inside of this compact group, unitary group. And then finally, well, this guy is a local system of finite monodromy. And finally, you can just analyze the local monodromies to check that the finite group has to be a complex reflection group. And that was the theorem. Okay. Okay, I have some things about the condition on infinite local monodromy, but maybe let me not say too much about that. Okay, so let me just try and conclude and say some open questions that we weren't able to resolve. So again, the upshot is that we classify all of these rank 2 MCG finite local system on P1 minus n points. And the classification is basically what Hossein was saying, that either, well, you get a lot of them by taking a finite monodromy one and applying middle convolution. And then there are also these pullback types, which are classified by Diarra, and those are everything. That's our theorem. Again, assuming that one of our matrices is infinite order, and I haven't told you why that's important. So our results recover the one I mentioned due to Dubrovin and Matsoko in 2000. And we almost give a complete conceptual classification of the algebraic solutions to Painlevé VI. So I said that this classification of MCG finite local systems in P1 minus 4 points is equivalent to finding algebraic solutions to Painlevé VI. And that's what we give. If you like, this can also be thought of as some kind of classification of rank 2 representations of a finite index subgroup of a braid group. Okay, let me not say too much about that. And finally, we just said is the monodromy of the middle convolution is some complex reflection group, but we haven't checked all of the complex reflection groups to see whether this is true. I think maybe Daniel has some students who are working on that. So it'll be interesting to just finally find all of them.
But I think that's basically done now, actually. So
okay.
Hopefully in a couple of weeks it will be.
Great. So soon we'll know everything. Okay, so the most kind of obvious question is, how do we get rid of this condition of AI being infinite order? And unfortunately, we don't really know how to do that. And then obviously, also for higher rank local system, and it seems a bit tricky. Okay, so that's, I think, okay, so I also say something about, instead of just looking at MCG finite points, you can ask about MCG finite subvarieties. So again, there are some easy examples that you can produce, and you can try to classify not only MCG finite points, but MCG finite subvarieties of this Xn. Okay, so thanks very much for your attention. I'll stop here.
Okay, thank you very much.